not worth investing. It's not worth putting in more staff time and resources to do this expensive lab testing. So if they do, show some nominal response to something, then we'll go ahead and do the concentration ramps. We'll do the temperature and relative humidity studies. We'll do the interference studies. We'll do what's called an outdoor simulation, because this is our best shot at doing outdoor testing for now with VOC sensors. And then we'll do a final concentration ramp, which is just repeating phase 2, because there's some drift effects that we want to kind of capture. If you test it at the beginning and then, maybe a month later, what is the response? Maybe the response changed because it just got a little bit older. And also the blend of gases that we use for testing, we do a benzene only gas, but also we do a 4 blend, ethane, 1,3-butadiene, benzene, and tetrachloroethylene. We do a 4 gas blend because VOC sensors, they are total VOC sensors. They just report a total VOC signal. And so it probably makes sense to test them against a blend of species. And we have these 4 species chosen mostly for historical reasons. The US EPA, they did some very early study in 2014 where they tried to test out VOC sensors, and they used 1,3-butadiene, benzene, and tetrachloroethylene. And then when we got around to finally doing our testing, we also added ethane. And that way we have, representation of different classes of VOC species. So your short alkanes, your aromatics, your chlorinated compounds, and then what is 1,3-butadiene? I forget. Some other kind of representative class of VOCs that you can find in the atmosphere. And also a few of these, they have relevance to human health. So benzene exposure, 1,3-butadiene, tetrachloroethylene, terrible things to be exposed to. So that's why we have those gases. We have a lot of commentary from people who want to use VOC sensors for oil and gas refining monitoring. They want us to use BTEX, benzene, toluene, xylenes in our testing protocol. That's certainly something that we'll consider in the future. It's just at the moment, this is like where we're starting off at. And yeah, maybe BTEX in the future. We have other folks saying you should include a blend that has dozens of species, and that would be wonderful. We just don't have that kind of staff time to integrate, to do the kind of analysis when it's a couple dozen species in a blend of gas. And so, the newer testing procedures, they get more and more complex, right? So now we're reporting more metrics because we do more of these tests. And so it's not only just the traditional metrics, but also, the success rate at detecting transient events, and maybe the response, the change in the sensor over time. And then maybe doing some ANOVA or something to figure out what are some explanatory factors that these VOC sensors that explains the behavior of these VOC sensors. Here's a list of the reference monitors that we use for our VOC sensor testing. So we have a non-methane hydrocarbon analyzer that provides about 1 minute time resolution. This is basically total VOC. So this is the most comparable kind of measurement for low-cost sensors because they're reporting every minute and they're reporting a total VOC signal. We also have a GC-FID, and we've modified the method so we can get about 20-minute time resolution for the 4 species in our blend. This is more of a check. It's more of a sanity check that we can compare our non-methane hydrocarbon monitor to. This is a sanity check to make sure our reference monitor isn't performing crazy and then we're doing an unfair judgment against a sensor. And then we also have reference monitors for these other gases, because for certain VOC sensors, ozone and NOx, they could be interfering species. So we also do interference tests with these other species, and that's why we have those monitors as well. And so we've only published, I think, 3 or 4 VOC lab reports so far, hopefully more soon. But let me just walk through a typical VOC sensor lab report. So this one is an Aerocall S500 PID, which is a photoionization detector. Typically, VOC sensors, they're either going to be MOX or PID sensors. So again, we provide some background on the situation of our testing, some information about the product, information about our reference instruments, a photograph of how they were set up. This is, what is this? Oh, this is just a comparison of our reference monitors. So this is our GC-FID against our non-methane hydrocarbon analyzer. So this is just a check before we start testing to make sure, do our 2 reference monitors agree? And, that way we're not gonna start the test with a poorly performing reference monitor. This is that phase one, that transient event test. So, this is a very simple test. Just puff in, episodes of VOC and just make sure that the sensors respond. So in this case, fortunately, these sensors, they did peak at the same time as our reference monitors did, and of similar magnitude too. So that's really promising. And then here are some concentration ramp time series. So for our concentration ramps, we do a low concentration ramp and a high concentration ramp. And that's because of our two different reference monitors. So for ambient usage, you actually want to know what the performance of a VOC sensor is at very low concentration, because that's your typical ambient concentration. So for these low concentration ramps, we're only going up to, anywhere from 15 or 60, let's see, like 15 ppb up to about 1.5 ppb. And so for these low concentration ramps, we have both our non-methane hydrocarbon data set and also our GCFID data sets, which, oh, thank you, our GCFID data sets. And so thankfully, those two reference monitors agree well. And it looks like these sensors, two of them, the green and the yellow one, they seem to be, doing okay, but then the blue one is quite different. It has a very low response. And then we also do a high concentration ramp because a lot of these VOC sensors, they're not very sensitive to low concentrations. They perform better, at higher concentrations of VOC based on their manufacturer specifications. And so we'll do a high concentration ramp as well, where we only have the non-methane hydrocarbon analyzer data. And that's because the non-methane hydrocarbon analyzer, it has that working range to go up to higher ppm levels of VOC. Our GCFID, it's because of our column and the method, it doesn't allow us to use the GCFID for higher concentrations. So in this high concentration ramp, you can see that the sensors, they are closer to the reference values. We see one of the units is, chronically underreporting. And so you can see the scatter plots for the low concentration ramp and the scatter plots against the reference in the high concentration ramp. And so at least, these PID sensors, they're quite linear to the reference measurements. So that's still a positive sign. Okay, can we zoom out? Thank you. Okay, and then we'll also do some climate interference tests. So this is an example of a relative humidity interference. So we'll have our reference monitor in red. We keep the ppb at the VOC is at 4 ppm constant. And then we'll change the relative humidity in the chamber. We'll go from 20, 40, 65, 80% humidity. And then you can see that even though our red, the reference monitor response, it's stable no matter what humidity you put into the chamber. You can see that the clear effect. And then we also do some temperature tests because some of these sensors, they're very sensitive to temperature. And so here's an example of let's see. So we start at 20 Celsius, we'll go cold to 10 Celsius, we'll go hot to 30 Celsius, and then we'll come back down to 20. And you can see that, there was some kind of, our reference monitor did something funny when it went from cold to hot. It was probably trying to do some internal adjustments to the sample temperature during that time. But it's still relatively flat, whereas the sensors, you can see they were quite sensitive to these temperature changes. And then we'll also do gaseous interferent studies. So this is an example of where we have a constant VOC concentration from our reference monitor, and then we'll have 0 ppb of ozone. Then we inject 50 ppb of ozone, 100 ppb of ozone, 200 ppb of ozone, and 400 ppb of ozone. And then we see whether the sensors, if they are impacted. And in this case, because they are PID sensors, we don't expect them to be susceptible to the influence of ozone. And so we kind of see that reflected in the result where the PID sensors, their response is flat, no matter how much ozone we put in. And then we see that unit 1, by the time we got to this test, it was just kind of dead. It wasn't really showing any data at all. But that's normal, And then, but funny enough, when we do the CO interference test, the blue unit, it came back to life. Who knows? And these units, they were not susceptible to carbon monoxide, again, because they're PID, so we don't expect that. No. Okay. So one of our later tests is what we call an outdoor simulation. We do recognize that it is of most interest of how these sensors would perform in an ambient condition, but at the moment we're only doing laboratory tests. So our kind of way to address this is to try to simulate to the best of our abilities an outdoor, a day's worth of outdoor conditions in Los Angeles. So that means creating a chamber condition that's pretty cold and humid. So at nighttime, our temperatures are like 10 C and our humidities are high and we don't have any ozone. And then when the sun rises, it gets a little warmer, it gets a little drier. And then as the sun rises more, then you get the photochemistry with the NOx and the VOCs. So then you start getting some ozone. So we'll inject some ozone. And then at the peak part of the day, when it's the hottest, we'll have temperature to 30 and we'll have the humidity pretty dry at 10%. And then by the peak of the day, that's also when we'll see our highest ozone concentration. So that's why we also inject 100 ppb of ozone. So we're kind of doing all these different combinations of components that are simulating a typical Los Angeles day to see how the sensors. Sorry, I forgot to mention. We're also ramping our VOC levels high, low, high, low, high, low to kind of get every single combination at the temperatures, humidities, and ozone high and low VOC concentrations. So that's why you see our reference monitor in red. That's why it's going up and down, up and down. That's intentional. And then we're also trying to track how the sensors follow the different combinations that we've tried to simulate for outdoor. And then we can run like something like ANOVA and see, how much of the sensor's response is explained by VOC concentration, by temperature, by humidity, by ozone, and how much is the residual signal. And thankfully for this particular VOC sensor, most of the sensor response was due to VOC and not due to, other weird parameters that you don't want to be influenced by. And then also we'll do a second ramp where we repeat one of the earlier phases, the ramp, and then we just compare, what was their scatter plots at the beginning. So phase 2, the initial ramp, in blue, the beginning, and then by the end of the testing, how that response changed, just to give it a kind of a, curb your expectations of the lifetime and usefulness of some of these VOC sensors. Okay, something that I hope to get on the road soon is our systematic mobile testing. We've done 3 iterations of mobile testing platforms. We've done some preliminary investigations. This is probably the most staff time and resource intensive effort. So, at some point in the future, we will start doing this on a regular basis for sensors. So right now we've decided that if a sensor did well in the field and if it did well in the lab, then okay, we will devote the resources to test it on the car now. Or we are seeing some products come on the market where they are specifically designed for mobile testing. So some of the sensor products, they have like an aerodynamic housing and they have a magnet so you can just stick it on the top of the car. So if they're specifically designed for mobile use, then we'll also test them right away on the car. And so what we do 4 different test phases. So the first one is in cabin, because we know some people want to use sensors inside the vehicle to monitor. We'll also do a controlled flow sensor duct, which is this thing. It's like a long duct and it has like a fan and, has an inlet and controls the airflow in. So this is probably more of a academic university kind of exercise if you want to do mobile monitoring with sensors to put them in a controlled flow duct. We also have another testing scenario where it's in a partially controlled sensor box. So this is probably more appropriate for also university academic exercises, but maybe more getting into the community use of sensors. You have a sensor, you want to partially protect it from the wind and the turbulence and from the sunlight. So you'll put it in a box, a protective box with a hole for air to come in and a hole for air to go out. And that kind of, you can still get some measurements that way while protecting the sensor. And then finally, we'll test the sensors completely unprotected on the rooftop.